we are going to discuss thermal comfort. What are the conditions for thermal comfort? First is the body has to be in heat balance. This is one of the very important requirement. Next one, the sweat rate should be within comfort limits. Mean skin temperature should also be within comfort limits. The heat balance is necessary, but not sufficient conditions for comfort. This is very important statement, that balance is definitely necessary, but not sufficient condition for comfort. The body could be in heat balance, but uncomfortably hot due to sweating. So, if the sweat is getting generated too much, we will not feel comfortable also, or it could be uncomfortably cold due to vasoconstriction and low skin temperature. But the main points are the heat has to be balanced, sweat rate and should be within a comfortable limit, and the mean skin temperature should also be within comfort limits. Let us look at this point first, thermal equilibrium. See, the body is continuously generating heat, which we call metabolic heat. So, metabolic heat production is, let us say, M, and then if we do some work, for that we also spend some energy, and that energy is provided by the metabolic heat that the body generates. So, the net heat that will be there will be metabolic heat production minus the mechanical work done by the body, that is the amount of energy you spend for doing some mechanical work, which could be simply walking or sitting or doing some other activity, reading or jogging or playing, whatever, all of them are basically mechanical work, except if you are sleeping. So, this difference between these two, that is the heat that the body has, excess heat now, this heat has to be dissipated, and therefore, this should be equal to total rate of heat loss from the skin, which we call QSK, and the rate of heat loss from respiration, because we are breathing continuously. So, we are taking the air in from outside and we are exhaling the air also. So, these two should remain balanced, that is whatever excess heat the body is there in the body, that should be balanced with the heat loss from the skin as well as the loss because of respiration. So, we can write this in the form of a mathematical equation, m minus w should be equal to QSK plus QRS, that is heat loss because of respiration, RES stands for respiration and SK stands for skin. Okay. So, let us try to find out what are the various ways by which heat can escape from the skin. So, m minus w is QSK plus QRS, and QSK we can write in the equation number 2, which is ESK plus R plus C plus K. We will come to know what are these letters are going to indicate. ESK stands for the evaporation heat that is lost from the skin, which has also two components. One is ERSW and EDIF, that is evaporation loss because of sweating and evaporation because of diffusion. and QRS similarly has two component CRS and ERS. So, you will be interested to know what are these stands for. So, QSK we have already stated, rate of heat loss from skin, QRS rate of heat loss through respirations, ESK the rate of total evaporation heat loss from skin, and QSK components are other than ESK we have R plus C plus K. What is R? R stands for radiative heat loss. Through the radiation we are going to lose some heat continuously. C is the convective heat loss, because air is taking away part of the heat from our body as it is blowing over the skin, and the third one is K. K is the conduction loss. Air is a poor conductor, we all know, but still there is some conductivity and some heat will be lost because of conduction, even though it is very, very low. CRS is what? Is rate of convective heat loss from respirations, and ERS is evaporative heat loss due to respirations. So, these are the various equations which are in a way informing us that what are the various components of loss which could be there, and if we want to calculate the amount of loss of heat from the body, we have to find out all these losses one by one, and then we have to see what could be the total loss. So, and then we have to see whether the total loss of the right hand side is equal to the left hand side, or is it more or is it less. We go to the next slide. Now, substituting these equations 2 and 4 in equation 1, we can write m minus w equal to this as it is written here. From there we go to equation number 6, that is, if there is an imbalance between the heat generated by the body and whatever heat is left in the body even after doing some work, and the amount of loss which is possible from the human body in a given circumstances, because how much will be lost from the body will depend upon what is the environmental conditions. So, sometimes there is a chance of imbalance, not only sometimes, most of the time there will be a chance of imbalance, and therefore, what can happen? The difference between these two is going to the amount of heat which is going to be stored in the body. So, the value stored is known as S. So, S could be what? If they are in balance, then S will be 0, that will be thermal equilibrium. So, S is 0 mean heat is balanced, that is we are in thermal equilibrium and the person is going to feel comfortable. The other possibility is S is greater than 0, that means that I am losing less heat than the body is generating. In that case, the value of S is going to be positive, more than 0, that means the heat is going to accumulate in the body, and as a result of that, what is going to happen? The skin temperature is going to rise, and a time will come when we will feel uncomfortable. The other thing is, the third possibility is S is less than 0, that is the possibility of losing heat is much more than what is being generated, which is generally happens when it is winter time. In that case, the body is going to lose more and more heat than it is generating per unit time. As a result of that, the body temperature will go down and down. That is what will going to happen, and that will be some consequences for that also. So, clothing insulation required for thermal equilibrium is therefore, that S has to be 0. So, that is the equation 6 that we have written earlier, the same equation I am writing it back again. And what we have done now is that, because the conduction heat loss is generally very poor, because air is a very poor conductor, basically it is insulator. So, we can, all practical purpose we can consider K to be so small that we can neglect from our equations. And what is left now is m minus w will be E s k plus r plus c plus c r s plus E r s. This is what is will be your the equation now. Therefore, the R plus C, that is the radiation heat loss because of radiation and because of convection, should be equal to m minus w minus E r s, C r s and E s k. And we have already seen what are these quantities. M stands for what, W stands for what, these are already stated earlier. Now, what is R plus C? R plus C should be equal to T s k minus T c l by I c l r. T s k stands for the skin temperature and T c l stands for the temperature of the clothing, and I c l r stands for the insulation value of the clothing material. Therefore, if the body is covered by some clothing, then there is an insulation value for the clothing, then we can say the heat loss because of radiation and convection put together, this should be how much? This should be temperature difference divided by the value of the insulation of the clothing material that we have on our body. So, R plus C will be equal to difference between the skin temperature and the clothing temperature divided by the clothing insulation. Therefore, for clothed body, the clothing insulation required will be T s k minus T c l divided by R plus C. I r q stands for clothing insulation required. That means, it is basically I c l r. Clothing insulation required, I required, we write it I r e q, I required will be T s k minus T c l divided by C plus R. C plus R is what? M minus W minus E r s minus C r s minus E s k, that is what is written here. And this is for the clothed body. For the unclothed body, the body is naked, in that case the clothing insulation which we will be needing, or the insulation that we need, in that case the temperature of the clothing will be replaced by temperature of the air, and we can find out that for such a body how much insulation is actually required. So, these equations can be used to find out the insulation value that we need in our clothing. When you try to design a clothing, the first thing we need to know how much insulation is required if it is for winter garments. Then comes that if I want to have so much of insulation, then what should be the fiber I should use, what should be the fabric, what would be the DSM of the fabric. These are the second stage. First is to find out the requirement part. Unless I know the requirement, how can I design? So, for any design activity, we need to know the requirement first. So, some basic requirements are needed to be either available to us, or if it is not given to us, then we have to find it out by doing some research or by doing some analysis. Many times the technical requirements may not be available. Some qualitative requirements will be told to us, which are not really scientific in nature. Like say, if I say I have to develop a clothing which will protect me from cold of Delhi, only this much is, a layman will be speaking in this language. Now, we need to find out therefore, that if somebody needs a clothing, or a company wants to develop a clothing, suppose it is jacket only, which needs a person to be protected from a cold which is generally experienced in Delhi in winter. Now, the actual glow value that is required in that particular jacket then needs to be worked out. This value will not be given by the customers or those the users. The users will only say that this is what he needs. The technical requirements needs to be found out by the designer, by the designing team. Therefore, we need to know what is the glow value that is required. Once we know that, the next step comes how to get that glow value in a fabric. So, okay. So, now we will do find out some exercise we will do just to show you how various equations that we have discussed in last few lectures, how to make use of them to calculate certain design parameters or design variables. First, let us start with this example. What this says? Now, let us say an example in which a man is resting in a room where the temperature and humidity are 21 degrees centigrade and 50% respectively. Okay. The metabolic heat generation is 50 kilocalorie per meter square per hour. There is no air movement in the room. What will be the insulation requirement of his clothing to feel comfortable? Skin temperature has been chosen to be, let us say, generally it varies between 33 34, we may choose a value 34. Now, you know that I have given you earlier the definition of glow value. If you look at that particular slide, what is the definition of glow, then you will find that to make a person feel comfortable, if he is sitting in such in a room where the temperature is 21 degrees centigrade and he is generating a body heat which is 50 kilocalorie per meter square per hour, then the insulation that he needs to feel comfortable is known as 1 glow. Now, can I really derive it now? We will see that in this situation, whatever has been stated as a part of definitions, can I really derive it or not? So, we will do a simple exercise. So, we know that IRQ equal to TSK minus TA by M minus W, ERS minus CRS minus ESK. W is 0 because the person is not doing any work. So, in this case, the W value, this value is 0. Metabolic heat generation in terms of what we have to find out. So, 50 kilocalorie per meter square per hour. What is the typical skin area of a human? The standard body surface area is taken as 1.8 meter square. Now, different people have different, they are body shape, different heights. So, the values will obviously vary from person to person, but as a standard it is chosen at 1.8 meter square. So, the 15 to 1.8 by 3600 will be the heat in kilocalorie that he is going to generate per second. So, this will be kilocalorie per second. For the whole body 15 to 1.8 divided by 3600. Now, this has to be converted into watt. So, kilocalorie multiplied by 1000 is calorie, that multiplied by 4.19 is a constant you can find out from some standard textbook. If we multiply calorie with 4.19, we get joules per second. The joule per second is the watt. So, that will be 105 watt of heat that will be generated. So, the whole body is going to generate 105 watt of heat. If he is not doing any work, this much heat will be generated by the person. The next is we need to know, see if we go the previous equation. So, we have found out the value of m. Now, we need to know ERS, CRS and ESK. Okay. So, we are trying to find out ERS and CRS, these two together now. So, there is an equation, empirical equation which has been given, and probably I have stated also in some lecture. CRS plus ERS is given by this empirical equation which is stated here, that is 0.0014 into m. M is the metabolic heat that the body generates into 34 minus T8 plus 0.0173 m, 5.87 minus Pa. Pa is the vapor pressure. So, to find out Pa, so Pa and PSA are connected by this formula, that is by relative humidity, and relative humidity value is given here, which is 0.5. So, to know Pa, I need to find out what is PSA first, and if I know PSA, I can find out immediately Pa, because relative humidity multiplied by PSA will give me the vapor pressure in the environment, in which the person is going to stay. So, to find out first PSA, there is a formula, this formula also has been stated earlier. This is the equation you use, where Ta is the temperature of the room, which is 21 degree centigrade. We have to this. So, we in this equation we only replace Ta by 21 and find out this value, and this will give you a figure 2.48 kilopascal. That is the vapor pressure near the skin when it is saturated. Saturated vapor pressure near the skin at the temperature of the air. So, from there we can find out what is the Pa value. This is in a saturated state. So, in normal state, this value is going to be this 2.487 multiplied by 0.5 will give me the pressure in kilopascal. Now, I put these values in the equations and simply substitute the values of temperature, substitute the values of the vapor pressure, we get a figure 10.32. That means, the respiratory system, that is because we are breathing in and breathing out, we are drawing the cold air, because the person is sitting in 21 degree centigrade. So, when he is breathing in, he is inhaling cold air, and the cold air is going inside in our lungs, and then it is getting converted, it is getting some heat, temperature is rising. So, this cold air is getting heated by the body, and at the same time there is some moisture also being released as we breathe out. So, when you breathe out, there are a lot of moisture that moves out through our nose, which is very common. We see the fogging in our spectacles, especially in winter. So, this fogging is because through the nose, when he is breathing out, whatever vapors are moving out is coming and settling on the glasses and getting condensed, and therefore, we get a fogging effect. Anyway, so the breathing in, breathing out, through that, this is the quantity of heat that is we are actually losing, that is so much of watt, not per meter square. So, the heat is in watt. Then the other one is that from the skin itself we are all continuously generating moisture. The skin through diffusion process, the moisture is escaping continuously from the skin. And how much is that moisture? Generally it is told it is 600 gram per day that has been reported, which is equal to 25 gram per hour, and the heat loss because of this will be how much? 25 gram per hour. We find out 25 by 3600, that is gram per second, and then converted it into by the latent heat 580, that becomes joule, then multiplied by 4.1119, it becomes watt. So, it is equivalent to 16.87 watt, that is 17 watt. So, that body is losing 17 watt of heat because of generation of moisture from the skin, which is insensible moisture, we do not come to know also about it. So, the heat that is we lose because of radiation loss could be there also. We can also calculate that separately, but there is no need to calculate here for this particular situation. We know that therefore, if we want to find out what is IRQ from this equation, we put these values here, that is how much insulation is required for the clothing. So, 105 of heat the body is generating, minus 0 is the work done, ERES is 17, and this total of these two is 10.32. If we do it, TSK minus TA is how much? 34 minus 21, because TSK is 34 and TA as given here is 21. So, TSK minus TA is going to be 13. So, 13 by 77.7, which will give you 0.17167. This will be the requirement of the IRQ, degree centigrade meter square per watt. This is the insulation value of the clothing that I need, so that only 77.7 watt of heat can be lost, not more than that. So, this is equal to 1.07 kilo, close to 1 kilo. So, the requirement of the clothing to make the person comfortable will be 1.07 kilo of insulations. Now, this may vary from person to person little bit, because metabolic heat generation may also vary from person to person. So, just to give you an idea that in a situation like this, when a person is sitting in a room where the temperature is 21 degrees centigrade and the person is naked, there is no clothing on him and the skin temperature considered to be 34 degrees centigrade, relative humidity is 50%, then to make him feel comfortable, we need a clothing whose insulation is going to be either 0.167 degrees centigrade meter square per watt or which is equivalent to 1.07 kilo, which is close to 1 kilo. Okay. Now, we will take another example, design of an ensemble for a person for a kilo value of 1.20. Let us say we want to develop a ensemble. An ensemble means a collection of garments which we use. So, what will be those different items which a sum of items will make an ensemble. So, if I want the total ensemble value is going to be 1.20, how to design it? First of all, the principle we have to remember that the whole body has to be covered by appropriate garment items. That is, a human body is not a point. It has a length dimension, it has a width dimension. So, the entire body has to be covered by the garment items. The insulation provided by the ensemble is generally less than sum of the component garments kilo value. This is important, that if I know the kilo value of the items that we generally use and we choose them one by one and make a sum of them and sum of the kilo values of individual garments, if we do, the ensemble kilo value will be less than that, because insulation may not be distributed evenly over the entire body and addition of garment increases the surface area for heat loss, and therefore, we know this is the equation which needs to be used, that is ICL, the total ensemble kilo value ICL is 0.82 sum of ICLI kilo values of individual items. This is the equation that has been given through some empirical study by some standard institutions. So, if this is true, then we can find out what should be the required total insulation, that is sum of ICLI is going to be ICL divided by 0.82, which is 1 point, let us say, okay, sorry, I have made one, this should be not 1.2, let us say 1.1, this is 1.1, because this value has been chosen as 1.1. This is basically printing error. So, 1.1 by 0.2, that means it has to be 1.34. The sum of the insulation value of the individual item has to be 1.34 kilo. That is what it has to be. So, this much kilo value we need. Now, here we have chosen a set of items to cover the entire body. So, a person needs these items to cover the entire body. He needs a socks to start with, shoe, underwear, undershirt, shirt, trouser, a sweater and a jacket. And what happens is the value in this table, this has been given by some American standards. by studying the clove value of the garments on mannequin, these values have been quoted and which are used. Like for underwear, some items are given and corresponding thermal insulation values are given. If you look at this table, underwear, shirt, trousers, dresses, skirt, boiler suit, sweaters, jackets. So, some items have been chosen, 42 items are here and their thermal insulation values are given. So, this is table is it for us, it is a kind of database. We make use of this table to choose items, so that we can cover the entire body of the person and get our desired value of 1.34. So, we have chosen these items: socks, shoes, underwear, undershirt, then a shirt, now a trouser, a thin sweater and jacket. And clove values have been given, this has been taken from the table, and if we add them, the sum values are stated here, we reach a value 1.33 is close to 1.34. That means, if these items are chosen, the entire body almost gets covered, except which area? Except the head, there is no cap is required, and the face part, nose, this area we have not really covered, and the palm area is not covered. So, this has been left. If I use this, because these are the areas which we cover in the end in case we really need further. We get a value 1.33. So, these standard values of the clove can be chosen from that table and say this is the ensemble, we have 8 items in the ensemble to give him a clove value of 1.33, and this will actually result a clove value of 1.1 finally. Now, one can choose items in such a way that could be another answer also. So, if I go to the next this slide, you will find option A and option B. Option B, if you see again we have chosen 8 items, and you see the figure, option A gives me 1.33, option B also gives me 1.33, but there is some items which have been changed, like previously we used socks, normal socks, we have used thick long socks whose clove value is more. So, whatever see in the table option B table, wherever it is red colored, these items have been changed. Earlier it was a normal shirt, we have replaced it by a flannel shirt with a higher value of clove. Then trouser, it was normal, now we have gone for a lightweight trouser, clove value little less than the previous one. That was a thin sweater, this time sleeveless vest, 0.12, little less in terms of that's clove value. Jacket is remaining same, sum total is again 1.33, here also 1.33, option A, option B, that could be option C also. So, there is various possibilities are there, and if these items are chosen so that you arrive at the final figure, then we will say that this is how the ensemble can be designed. So, if I know the clove value of the ensemble, then we can make use of this table to find or to choose the items. So, these are generally the items which are of general in nature, and they have been tested on mannequin, and then these values have been quoted by standard institutions, and these are there. This becomes our kind of database which can be used. Okay. Now, after this we go to another one. Calculate the claw value of a trouser, that is a short trouser. How do I find out the claw value of a short trouser? Now, this equation is there. This also has been stated. These have been given. Is an empirical equation. This I claw or I claw is 0.095 10 to the power minus 2 A cover, that is the percentage of body area which is covered in terms of meter square degree centigrade per watt, or in terms of claw, what we have to do? We have to divide 0.095 by 0.155. We get the value in claw. So, if this is what is formula is given, is empirical equations, we can make use of them to find out the claw value of a trouser short. Now, a short trouser, a trouser is going to cover the thigh area. So, percentage body covered by thigh is around 18.4%. So, that means, if I want to develop a short, the percentage body area it will cover is around 18.4%, close to that. Now, percentage of thigh area that will be covered by the short, out of that thigh, entire thigh may not be covered by the short, because it is short trouser. No? So, we can assume that let us say 55% area is covered by it. Therefore, the body area covered by the short is going to be 18.4 multiplied by 0.55, that is 10.12%. That means, this short is going to cover around 10% of the entire body area. The whole body area. In this particular table, this is a female mannequin. The total body area of the mannequin is 1.588, and this data has been given with respect to a mannequin, is considered to be 100, and accordingly the different parts of the mannequin area has been quoted here in this table, and we are using this particular table to get an initial estimate of the claw value of a trouser. The trouser, therefore, which is short, is going to cover only 10% of the body area, and therefore, the value of the insulation value is going to be 0.61 into 10 to the power minus 2 into 10, because 10.12% is covered, that gives you a value 0.061 claw. So, short trouser is going to give you a claw value using this equation is around 0.06, and if we take from the standard table, you will find a value which is close to 0.06. So, it may vary a little bit, it may be more or less depending upon the total. If the trouser is a little longer, it covers the entire thigh, then the claw value is going to be more. So, what matters is the amount of the body area which is covered. So, we have to know what is the body area that is being covered it, and that body area is what percentage of the total body area. Then another one example, calculate the clo value of a jacket. Let us say we want a jacket and we want to know what is the clo value of the jacket. So, if I think of a jacket, what should be the clo value of a typical jacket? Now, the right hand side a table has been given, where again from the mannequin these areas of different parts of the bodies are shown here, 1, 2, 3, 4, 5, 10 up to 20 different parts of the body. The areas are given here, and this was taken from a paper, research paper by these persons, and we make use of this, let us say in this case. Calculate the clo value. So, first of a jacket. So, first what we need to know, how much body area the jacket is going to cover. So, total area of the jacket will be area of the chest. The jacket is going to cover the chest area, the shoulder area, the stomach part and the back side, plus arms, left and right upper arms and left and right forearms. Because you look at the way a jacket, you all know the design feature of a jacket, and how much, what are the areas which are covered by the jacket. Jacket is not going to cover the thigh or not going to cover the leg. Therefore, this jacket is going to cover the front part of the body till waist or little below waist, and the back part, and also the entire arm. So, we will try to find out first what is the area of the body which is getting covered by a typical jacket. So, the corresponding values we will collect from this table. So, percentage body area covered is total area of jacket divided by total area of the body. And so, you find out the values of the chest, shoulder from this table. Chest is this much, shoulder is this much, stomach is this much, back is this much. So, these values are stated here, and in terms of proportion I will divide it by 1.72, that is the whole area of the body. Standard we choose generally 1.8, but this mannequin has 1.72. Then left and right upper arm. So, left and these are upper arms are values are 0.07, 0.07 into 2, and left and right forearm 0.06 into 2 divided by 1.72 into 100. So, that is the body area which will be covered, that gives you a figure around 40%. So, a jacket is going to cover 40% of the body area. If this value we use in this equation, we get a figure 0.24 clo. Okay. And let us now check, if we check it, the light summer jacket has a clo value of 0.25. So, jacket could be 3 different types of jackets, it has been stated here 0.25, 0.35, 0.30. So, and this is going to match with our 0.24 value. So, that is, it is giving you an initial estimate. Now, you may say that this is little we are missing one aspect, and that is the the thickness part. A jacket could be made from a thin thin fabric, and if I make it from a thick fabric, then the obviously because fabric is thicker, the flow value is going to be different, but this particular equation does not take care of the thickness of the fabric, which also should be taken into account, and therefore, for its typical normal fabric this is going to work. But if we go for a thicker fabric, then obviously the another aspect has to be brought in, and that is the thickness aspect also. So, therefore, there is another equation which can be used. One is first part of the equation 0.43 to the power minus 2 A cover percentage of the body area that the garment is going to cover, and H fab is the basically thickness of the item. If it is suppose if it is jacket, we need to know what is the thickness of the jacket. So, thickness can be put in, and here also the multiplied by A cover, the percentage area covered. So, one can relate thickness to GS. So, thickness has to be measured following a standard. So, the standard has been stated that based on the standard, that is so much pressure we have to apply, then we have to measure the thickness value, and from the thickness value and the percentage area that garment is going to cover, we can find out what is the insulation value of a garment made from that particular fabric. So, if the fabric remains same, that means if upon the fabric, suppose I make a short trouser, the insulation value is going to be less. Using the same fabric, if I make a long trouser, the insulation value is going to be more. Or if I make a sweater which is sleeveless, the insulation value will be less, but same material, if I go for a sweater where sleeves are there, then the insulation value is going to be more. So, what matters, the flow value represents the insulation in a garment form of a fabric. When a fabric is converted into a garment, then what is the insulation of this fabric of this garment? That is what we can find out, and that will depend how much body area is covered by that garment. If I cover less area, the flow value will be less. If I cover more area, the flow value will be less. But from the fabric, if you look at the fabric in isolation, the fabric may still remain same. The intrinsic insulation value of the fabric is not going to change, but when we transform the fabric into a garment, then depending upon how much body area is getting covered by that garment, the insulation value is going to be different. So, with this we complete or finish this particular discussion, that is how we can make use of some of these equations which are there to find out the requirement in a given situation in terms of the insulation value, or the designing of an ensemble also, or maybe the flow value of a garment. These things can be found out. I have not taken an example related to the thickness. So, if you have a, but if we know the thickness as well as the percentage area is covered by the garment, then we can also find out the what is the going to be the insulation. So, these are very simplistic, some examples we have chosen in order to make you understand. but we have these are all basically a situation where only dry heat is getting exchanged, but when the moisture comes into play, obviously there will be another dimension which has to be added to it. So, those things will be taken in future lectures also. So, with this we are closing today's discussion. Thank you.